Welcome to Kegs, Casks, and Cricks-in-Backs, the ergonomics of beer brewing and distribution. It's a discussion of how the brewer's back aches, why, and how did we get here anyways. This presentation features photos supplied by both Alan Brown and Doug Steele. A special thanks also goes out to the long-suffering Dr. Emily King Ph.D., Manager of Research at VHA Home Healthcare and Assistant Professor of Public Health at the University of Toronto. In particular, some of the images provided by both Doug and Alan are duplicates, and so may feature a double attribution. The earliest brewers would often consume beer from the same vessel in which it was fermented. This was often the same vessel in which it was brewed. This is still practiced in some rare instances today. We have found examples of clay pots that had a capacity for about 32 liters, and depictions showing them being split about 8 ways. Before we invented the beer barrel, beer was seldom moved far from where it was consumed. In the ancient period, it was more common to make beer where you drank beer. So breweries were often constructed next to ceremonial sites where beer would be consumed, or small home breweries were built into the home, as we see in some of the Roman villas. The practice of brewing where you drink for pure simplicity and ease of use continues straight through to this day. When it came down to getting your beer to go, the vessels we see employed tend to be a lot smaller than those we'd use today. We see things like stoneware cups, jars, jugs, being able to move beer in relatively serving-size containers. We also, in the ancient period, will see some use of animal hides, and as well bark buckets. Jumping ahead to today, we have the standard beer keg. The most common size of beer keg today is the half barrel, coming in at 58 liters, and the nearest metric equivalent at 50 liters. These sizes of keg were established in the early half of the 20th century. In between the ancient and the modern, we have the beer barrel being introduced during the medieval period in Europe. This allows beer to begin to be transported over much greater distances than before. When comparing it to the clay and mud-sealed amphorae that preceded it, the medieval beer barrel was a comparatively watertight and aseptic beer container. The fact that the beer could travel further meant that it did. This meant that the barrel of beer became a standard unit of trade during the medieval period. It is currently defined as 164 liters in the UK and 119 liters in the US. Of course, when we say standard and we say medieval Europe, we have to allow for a fair amount of flexibility. You're going to see variation happening even between coopers within even a single city, not to mention the impacts of recoupering a barrel on the internal volume. Nonetheless, we have a reasonable agreement as to how big a beer barrel should be. You may note that 119 to 164 liters is also a fairly large amount of beer. Depending on local custom, that could be anywhere from 200 to 320 servings. And I think this says a lot about how our beer was going to be consumed once it got to its destination. It may strike many as odd that the standard size of keg chosen in the 20th century is precisely half the size of a historical measurement of beer. After all, prior to that we have beer barrels being the most common, but we also have casks, firkins, half barrels, and pony barrels filling in the gaps between our standard beer barrel and then our beer to go, being poured from the barrel into the bucket, carafe, jug, or very large cup, if you will. So before the keg, beer to stay came in something big like a cask or barrel, and beer to go was dispensed from that cask or barrel directly into your cup, bucket, jug, whatever. This brings us back to why a half barrel, precisely. Many beer historians agree that the half barrel was thought to be a more convenient size by different industry players, but dominated mostly by big brewers and big beer distributors. And at this time, when we say big beer distributors, we're talking international. This focus on long-distance beer distribution really drove a lot of the decisions that impacted the choice of the stainless steel keg. Made now cylindrical rather than barrel-shaped, The new kegs were easier to stack and wasted, quote-unquote, less volume to airspace when packed tightly together. Coupled with this, we're seeing changes in consumption patterns that also feed into these decisions. Beer had to be shipped much further. It was often being shipped in bottles, which was heavy, heavy glass. But we also have the world population growing, and the small number of breweries we have in the 20th century brew more beer to match, which is consumed, again, over an even larger geographic area. We also see an increase in the generalization of distribution technology. We're seeing a higher use of diesel trucks, refrigerated or not, to deliver beer rather than specially built horse-drawn wagons, trains, and even canal boats. This is all tying in with the globalization of the beer industry to have great big huge beer distributors as well as great big huge beer brewers. A globalized beer supply chain is therefore more sensitive to small changes in the package shape, volume, and size than it is to smaller considerations like the impact directly on an individual worker. While not inherently evil, we'll see the impacts of this as we go through this discussion. So why do I think it's a problem? Well, I can tell you from first-hand experience that working in the brewery certainly deteriorated my already problematic back, but further than that, I looked around at my classmates from Brewers College, and a few years on, a distressing number of them had already retired from brewing, not because of the pay, not because they didn't love the work, but because their backs had given out. And that seemed wrong to me. You know, reflecting on the fact that the standard beer containers from the medieval period weighed at least twice as much as they do today, and likely even more than that, it especially seems perplexing that a craft that is centuries old, that we know has always been physical, but we also know had brewers working well into their 40s and 50s during the monastic period, how all of a sudden are we wearing out individuals in their 20s within the space of 3 years? Of course, when we say brewers are working well into their 40s and 50s, we need to also reflect that breweries of the past tended to be more generational than they are today. We tend to get collections of young people working at startups, or people funding it who tend to be of a certain age, and we don't have the same continuity that used to be present where we have apprentices through masters working in the same facility. So that same brewer who starts at 20 isn't necessarily doing the same work at 40. The old adage that many hands make light work applies here as well. We see more individuals per liter of beer, often owing to the physical requirements of literally every aspect of the brewing process prior to automation. Simply put, you have more people making less beer per person. You still have brewing being a hard craft, but you also see a difference in the competitive nature of the business. Modern breweries compete over the span of, say, a half decade or 1 to 2 years, whereas previously competition between brewers took generations. But all of those factors aside, the big one, in my opinion, is the fact that barrels were made for rolling, whereas with kegs our approach is to lift them. I've got a barrel wash line depicted here. We're going to get a close-up look in a minute. While the empty barrels are shown stacked, the barrels are shown as being rolled, either on their edge or on the bilge of the barrel, and we don't see many people engaged in the act of lifting them. You'll see in the background there's a man rolling the barrel on its edge hoop. You see rails for rolling the barrels along across the entire floor. In particular, this photo is of a Canadian brewery from the 1930s and 40s. The first thing you might notice is that there's actually 15 people in this photo, so there's actually lots of hands on the job. You'll also see in the background a mechanical assist, probably for lifting aids. You'll also notice that on the barrel wash line here, you'll see both barrels and casks, indicating a variety of package sizes being used. This is a photo of the Guinness barrel yard from the early 1900s. Not a single person in this very, very busy photo is lifting or using a hand truck to move a barrel. They are all being rolled or transported by mechanical devices or indeed by horse. I'd like to use this close-up to illustrate an important part of early brewery design. You will note that the loading dock for the beer barrels is significantly higher than the bed level of the train. This allows for full beer barrels to be rolled down onto the train and then properly arranged to be stable, and then for empty barrels to be rolled up and off, or if absolutely necessarily, lifted. At no point is it intended for anyone to lift a full barrel of beer. Going way into the back of that photo, we can see that there is one person among those dozens who might be lifting. But in my opinion, he's actually more likely a cooper working at a work table. Regardless of whether the cooper is lifting or not, he is but one of many, many, many individuals working at this facility, further reinforcing just how many more people were working per liter of beer prior to the intense automation of our industry. Let's stay at Guinness in the same period, but shift to their dockyards. In this photo from 1910, you can see absolutely massive beer barrels being rolled down to the ships on rails and then hoisted by cranes. Already in 1910, we can see the impacts of the early steps of automation. There are many fewer individuals working in this photo and a significantly larger number of mechanical cranes. Nonetheless, in the far left-hand part of the frame, we can still see individuals rolling these large beer barrels on rails so that they can then be lifted by the automated crane. But how do we examine barrel handling before the age of photography? In order to do that, we'll need to look at paintings, sketches, and etches. The emphasis on rolling rather than lifting barrels was hardly confined to Europe. I couldn't find a precise date for this painting, but I was able to establish that it was from between World War II and the mid-1970s. Titled Rolling Barrels Out of the Rack House, it depicts a machine designed to roll barrels automatically. When I first got the idea of using paintings and sketches to look at how people used to manipulate barrels, I initially thought that I would find that brewers were physically built differently, possibly because of a childhood of hard labor. Likewise, I thought there might be a special technique or something. I did expect that there would be a lot more casks being lifted than full-size beer barrels. What I found instead was a very, very small number of solo carries of casks or barrels of any type. In fact, these are the only 3 depictions I could find, of any realism, that showed people actually lifting barrels by themselves. And notably, in the center, man lifting a sake barrel, he's actually a strong man in a competition. I would also point out that in these cases, the cask is being lifted usually so that the load is centered in the body. The vast majority of depictions you see show people rolling barrels instead, and there'll be more of those examples coming up later. But this is a classic example of workers moving oil barrels. This is from 1869. Now that we've looked at why you probably shouldn't lift a keg, let's look at what happens to your body when you actually do lift a keg. For this section, we're going to be borrowing very heavily from the notes and slides of Dr. Emily King. Dr. King is a specialist on body mechanics in the workplace. Her particular focus is on healthcare workers and how their bodies are loaded when they move patients. More recently, we've collaborated on ergonomics in craft breweries. And everything we're looking at today is all cumulative loading. So it's the tasks you do repeatedly, not necessarily things that hurt you right away, but things that will hurt you over time. Acute loading and acute injury is a different thing, and that's sort of when your body goes pop, right? You'll notice these damages more sort of right away, and they'll hurt a lot. Acute injuries will sort of send you to the hospital the same day, whereas cumulative loading and cumulative injury, that sends you to the physiotherapist more sort of long term. This is a good depiction of the structure of the spine. We won't get too bogged down in details, but it's important to look at the disc portion. It acts as shock absorbers and allows for movement between the vertebrae. While damage to the vertebrae can be a cause of back pain, most of the back pain associated with long-term lifting and body loading actually comes from the squishy discs in the middle. Here we have listed many of the causes of chronic low back pain. They can include osteoarthritis, the degeneration of intervertebral discs, which is the point I'd like to focus on, as well as disc herniation, vertebral fracture, and the last point refers to the fact that pain is a psychosocial phenomenon, and the way your back relates to your work and your perceived function in society very much impacts how your back pain will present. In the past, when we've looked at safe working limits for lifting, we thought that the model looked more or less like this, that the load could be of a certain magnitude, your day of work would be of indeterminate length, and that there was just a safe limit that you could lift beyond which you would injure yourself. Our best new research has led us to realize that the previous model was not accurate. We now know that as the workday continues, your safe lifting limit actually decreases. A load that was safe to lift in the morning may not be safe to lift by the time you're ready to go home. This change in safe limits over the course of a workday is where a lot of injuries actually develop. The way we divide work in the modern-day brewery does not reflect this reality. Long workdays are very common, and we do not relegate the lifting tasks to the early part of the day only. They unfortunately must be spread throughout. This is a quick summary of what happens to your body during loading, and this will be where a lot of your pain actually comes from. As you start moving around and start loading your body, your ligaments will start to stretch, and as they stretch, they'll get some micro tears. Those micro tears will lead to inflammation. Both the stretch of the ligaments and the inflammation will lead to your discs having more mobility overall. The greater freedom of movement of the discs of the spine leads to an inherent instability. Now, the way your body reacts to spinal instability is often at a subconscious level. Your body rates very, very highly the protection of the spine. And so, when it's presented with spinal instability, especially under heavy loading, it reacts with muscular hyperexcitability. Without stiff ligaments to control the spinal instability, the body turns to muscular hyperexcitability as its only course of action to stabilize the spine. Now, muscular hyperexcitability means the muscles are working sort of extra hard, extra fast, and it leads to a feeling of something a bit twitchy, if you will. That extra hard work of the muscles results in a squeeze, and that squeeze leads to intervertebral disc compression. Now, once those discs are squeezed, you actually have once again more space for the discs to move. Now, if you stop working or stop, exercising or whatever you're doing that's causing all this activity and give your body time to recover, that's great, okay? Your body recovers and you can kind of go back to normal. But if you keep working, if you keep pushing on it, well, what happens is your ligaments keep stretching, you get even more instability, even more muscular hyperexcitability, and then even more intervertebral disc compression. And unfortunately, there's even more bad news. As you age, your safe lifting limit also decreases. So the same load that was safe for you to lift at 25 may no longer be safe for you to lift at 35, 45, or 50. And this runs contrary to the way our typical sort of hiring and ethos works. We view a job as a job and any employee as capable. However, the reality is we may be doing damage to those employees whether we intend to or not. As you may have guessed from the happy face, this represents a happy spine, a healthy spine, one that's not going to cause someone much pain. And what we see here is the discs have a freedom of movement up and down permitted to them by the ligaments, the muscles, and the intervertebral discs. the squishy bits in the middle. It's also important to note that the intervertebral discs are not static features. They're living tissue that helps communicate fluids as well as nervous signals from the spinal column and into the discs themselves. Damage to the surface of the discs inhibits their ability to remove wastes and to supply fresh fluids effectively. This inhibits the function of the discs of the spine. If we were to look at a living person's spine while they were working and moving, we might see the intervertebral disc look like this gray slab on the right. And eventually, as we're working and moving or exercising, we will do a small amount of damage to this disc, as represented by the red mark here. This is a small amount of scarred over area that won't behave like the rest of the tissue. Given enough time and rest, the small amounts of damage will heal. However, what is more typical is that we continue working and loading our bodies past our safe working limits. This contributes to additional damage to the tissue. A lack of recovery time after excessive damage leads to negative consequences. Eventually, damage upon damage leads to scarring over of the intervertebral disc surfaces. It's important to note as well that the damage already done leads to further damage being more likely because it increases the load on those parts of the body we haven't already abused. And the issue overall is not exactly the physical impact of the disc damage itself. That's not what's leading to the pain. It's the fluid issues that result from that scarring. Okay? It's the inability of the body to effectively transmit fluids and properly do its sort of waste cleanup in those areas. Scar tissue built up along the interior surface of the intervertebral disc leads to an inability to allow fluids to escape the disc and enter into the membrane, and vice versa. This leads to a lack of movement between the discs and an overall stiffening of the region. It also generally leads to more pain. By the time you've reached the point of significant scarring to the point of disc damage, your days working in that position are going to be numbered, as the length of time it will take you to recover may be prohibitive to you continuing the employment. These diagrams exaggerate the forces on an intervertebral disc to better illustrate the forces at play. What we have in normal loading is basically the weight of your body in an unloaded position. When we have compressive loading on the spine, this is often from when we are lifting something or bending and putting a squeezing force on the intervertebral disc. We also see damage occurring from uneven loading, where we have forces going side to side. This is evidenced by the sort of exaggerated bulge we see here. We also see damage coming from twisting motions, and that is the torsion type of loading. We will be looking at some of the compressive loadings as we look at lifting kegs in our analyses going forward. Now that we're armed with a little bit of knowledge as to how the spine is loaded, how injury occurs in the workplace, and how breweries are run differently now than they used to be, I think we can go back to examine some of the questions we asked earlier. So we know that in the past, brewers used to operate as a trade with novices through to masters represented in a single brewery, making them generational workplaces. And based on what our best research shows, we now know that our ability to lift safely decreases with age. So likely, in our past breweries, we are going to have significant lifting tasks separated between the different individuals on the job based probably on their age, among other things. When we're looking at a situation where we have more individuals per liter of beer who are going to be required to do the physical work of the brewery, we have more hands being available to do and share work. Solo lifts are less likely, and it's also more likely to have people spelling each other off so that the same worker isn't doing the same task all day long. And we know that reducing the frequency of the problematic lifts is key to reducing the lifelong injuries. So by reducing the number of solo lifts and increasing the amount of spelling off we might do, we're going to reduce the amount of recovery time we need between times we damage our spine severely. And to the last point here, While we have brewing being a hard craft, we have competition taking more time. More people with a lower production rate over a longer period means that there's simply less rush, more time to recover, and the number of permanent injuries we're going to do is going to be reduced for that reason. So rather than throwing in the towel, let's look at some of the solutions from the past that we could consider for today. This depiction, entitled Filling Beer Casks 17th Century, has a few things that I'd like to put a spotlight on. There's aspects of the brewery architecture, the use of lifting aids, as well as the way the work is organized that makes it clear that lifting is not something that people are doing at this brewery very much at all. In the background, we see at least one lifting crane, as well as a stout beam that I think may be an additional crane, but at any rate can be used for lifting as well. We also see that the brewery is immediately adjacent to a canal, which is a lifting-free source of beer transport. But also the work has been organized such that the barrels are being washed next to the river, where the water is being collected by the crane, and the beer barrels are not even being filled inside the brewery. The beer in this photo has likely been fermented nearly all the way to completion. We see the person sort of filling the casks from a large jug outside in open air. And of course, this is contrary to how we currently handle beer, where we keep finished beer far away from oxygen. I think it's likely that this is unprimed beer that they are putting in the casks to finish, likely to finish in the cellar of their destination clients. So the beer that has been processed in the brewery is probably going to be going through a series of gravity-connected vats and then dispensed into that carafe so that it can be manually transported outside into the casks. So the casks aren't even really coming into the brewery in this instance, nor are they being lifted anywhere. They're being brought out of the boat by the crane, they're being washed next to the river or canal, and then they're being filled outside the brewery. So some of the solutions to consider from this one is the architecture, the crane, and the overall handling concept that the barrels need never be lifted. Looking at another depiction from the 17th century, we see beer carriers, 17th century. Things to note here is not just the use of the lifting aid, nor the tandem lift, but also the use of the horse cart. The horse is pulling a beer sled, which is extremely low to the ground. Between the two operators is a lifting aid designed to share the load. Note that the carriers are unmatched in height, and this will likely put more load on one than another. So we see here the concepts of sliding the barrels, rolling the barrels onto the sled, and only lifting it at the last step when necessary, using a lifting aid split between two carriers. I'd like to contrast how they're loading their bodies in the 17th century depiction versus how we load our bodies when we're lifting a keg today. In the old-fashioned way of things, you use lifting aids and the load is brought close to the spine. Now we do see it being unloaded unevenly left to right, but it's not hard to imagine that they might have switched shoulders between kegs to further even out the loading. Our new ergonomic approach is we tell you to lift the keg or we call you a name. I can tell you I've experienced that firsthand, as I'm certain many of the rest of you have as well. Human body mechanics are quite complicated. However, teams of experts have worked long and hard to try to simplify the complex body mechanics into something simple and approachable. They managed to take the squishy connected mess of the human body, and they proved that you can simulate the compressive force in the lower back with a simple model just like this one. Now, this simple model doesn't look at other forces on the body like twisting, nor does it look at left to right symmetry. Okay, so if you're lifting more with your left side than your right, this diagram will not, and this model will not consider the difference in those forces. You may notice as part of the model that there is a term for body weight force. Obviously, worker body weight isn't something we want to control. However, we can say with confidence that workers that have lower overall body weights will observe less compressive back force. That may or may not translate into better back comfort. So that same individual who has less weight in their upper body, who may be experiencing less lower back compressive force, may also have a smaller frame with which to support that force. If we think of the spine as a column in this case, they have a smaller column to support the weight that they're bearing. So it's a bit of a give and take. It's a little bit like the difference between sort of spike heels and snowshoes in terms of how they apply pressure. This is in no way intended to promote any kind of body image. However, if you are someone who does a lot of lifting, especially for work, and you do experience back pain, you may wish to consider this factor when you imagine what a healthy body weight might be for you. Because the experts were able to successfully reduce the model to a simple lever, the analysis of the loading on the back actually becomes an almost trivial math exercise for experts. The tiny red lever you see at the back there, that is the lever that represents your lower back. Because it is a small lever, your body uses a lot of force to twist your back here. All of the push down that makes the lever twist needs to be matched by your leg force pushing up. Of course, once we had the model of the body lifting, the natural thing to do is to put it to good use. So they generated what's called a back load calculator. You input the body weight, the weight load, and how far away you're lifting it from your center of mass, and it tells you the load on the body. This is an example for a 50-liter stainless steel keg and a 90-kilogram person. The resultant compressive back force, the red arrow, is 5.9 kilonewtons, or 1,300 pounds of compressive force. The yellow arrow is the force supplied by your thighs, a whopping 3.6 kilonewtons per leg, or roughly 800 pounds. It's because of the nature of the body's lever and pulley system that your body has to supply more force than the keg actually weighs. Now this is ordinary. For a lot of loads that we lift, your muscles are contracting to a point where they're exerting much more force than the object might weigh itself. However, these are still extremely high numbers for the compressive loads on back and the support provided by the thighs. When I talk to ergonomic experts about the safe way to lift a keg, they sort of screamed and blanched when they realized exactly how heavy a full keg of beer can be, especially a rubber-bottomed one. And then when we add in the effects of slosh, it becomes a very dangerous system. On this slide, I've repeated the analysis for a 58-liter stainless steel keg with the same 90-kilogram person. The resultant compressive back force is 6.4 kilonewtons, or 1,400 pounds. The upward force per leg is 3.82 kilonewtons, or roughly 850 pounds. So that 8 extra liters of beer, which corresponds to about 20 extra pounds of beer, results in 100 pounds more compressive lower back force because of the nature of the levering system of the body. That's why the upper limit of keg weights gets to be so damaging. Here we've kept the 50-liter keg, but reduced the operator mass to 80 kilograms. The resultant reduction in body weight force corresponds to a significant reduction in the compressive back force as well as the thigh force up required. However, it is worth noting that an individual who may be lighter may also have less musculature and a different skeletal support to take the load as well. Going in the other direction, we're now looking at a 110 kilogram operator, or about 240 pounds, but keeping with the same 50-liter keg. The compressive force on the spine as well as the thigh force up is increased proportional to the person's mass and how far over they're having to lean to grab this keg. Now it is a little bit hard to estimate, but if you have, say, a big belly, the load lever effect will actually be even higher than this because the body mass that's leveraging over your center of mass will move as you lean over. So because that load isn't necessarily tight to your body, it's having an increased lever effect on your lower back. However, this effect is a little bit hard to evaluate. It simply means that if you have a more muscular, tighter body mass rather than a slightly flabbier one, you're going to experience less lower compressive back force. Let's take a look at the stubby 30-liter keg. We've gone back to our original 90 kilogram, roughly 200 pound operator. We have the same keg diameter, but the keg is much lighter, so the loads on the body are much reduced. The same effect we saw when we had the 58-liter keg versus the 50-liter keg, but working in reverse and to our advantage. The lower back force goes down to 1,000 pounds, or 4.8 kilonewtons, and the upward force per thigh goes to about 650 pounds, down from 850, or about 2.9 kilonewtons. If we reduce the keg even further to the 20-liter corny keg, we're not only reducing the diameter of the keg, but we're also reducing its weight. So we're combining both the leverage impacts and the weight impacts to greatly reduce the compressive back force on the body by changing the levering system that the body is having to use. The loads on the body are significantly reduced in this scenario. The compressive lower back force goes down to 3.4 kilonewtons, or 764 pounds, and the upward force per thigh goes down to 2.1 kilonewtons, or 470 pounds per leg. It's worth noting that the compressive lower back force and the upward force per thigh are essentially half of what they were for the 50-liter keg and the same operator. So in order to reduce the load on our backs, because of the levering nature of the way we're lifting the kegs, we need to reduce the weight of the kegs by even more than we need to reduce the proportional compressive load on our spines. Okay? And helping in that is going to be going to a smaller diameter keg. Even if you're using a 30-liter keg, having a skinnier torpedo style is going to provide less compressive back force than the stubby style. Returning to our depiction of the 17th century beer carriers, if we make a few assumptions about the authenticity of the depiction, we can actually start doing some analyses on the compressive backload. Again, for the model we're looking at, we are not looking at the left to right asymmetric loading that this style of beer carrying presents. However, given the style, it's not uncommon to think that they might have swapped shoulders during shift to offset this asymmetric balance. Okay? The cask weighs double the amount of a keg. Because of the wood weight and because of the beer weight, it weighs approximately double what a modern keg would weigh for the same volume of liquid. We also have an additional weight of a heavy oak lifting beam, with the chain being about 15 kilograms and some estimates being made for the size of the beam and how dense oak is. Because of the way they're lifting, the load is going to be centered over their body's center of mass. This means that the lever length that affected us so heavily before when we were lifting kegs is actually going to be 0 with these individuals. This greatly reduces the impact on the lower back and on the thighs. So even though we have a package that weighs twice as much, and we're splitting it between two beer carriers, ideally, we would think that the compressive load on the back would be approximately similar to what we have today, given that they're lifting about the same amount per operator. But when we actually look at the model, we see that we get 33% of the compressive back force in the tandem lift than we do in the solo lift. And this is solely due to the fact that they are carrying it with an assistive device that allows them to center the load over their bodies. Now, using this particular assistive device requires two individuals, and that naturally has some disadvantages. But if we look at this, it's the same people carrying the same amount of beer, we've just changed how they're doing it. If we assume that the lifting beam that they used was maybe pine instead of oak, that weight drops down to 10 kilograms, and the leg force drops further still. Note that the compressive back force is hardly affected, but that's because the load is so close to the center of mass. It has no leverage, and thus the compressive back load is essentially unaffected. The 50-liter keg solo lift produces 7.6 kilonewtons of upward leg force from both legs. The tandem lift only requires 3.3. This is more than a 50% reduction. And again, this is because there is less leverage required for the load, even though the load is larger. And that depiction of the tandem beer carry was far from isolated. When you look up for historical depictions of people moving barrels, this is what you find. Not solo carries, but teamwork and lifting assists. I really appreciated this color depiction from the Metropolitan London Archives. These two individuals caught my interest because we note that, first, the front carrier looks more like a fresh-faced young person, whereas compatriot looks slightly older. You'll notice that the younger person also has less worn clothing, and the other person has a slightly battered hat. This indicates that these two individuals are probably of different age and experience in the job, meaning that we're not piling all the same age group onto these heavy lifting tasks. If we take a closer look at their uniform coats, we realize that the leather overcoat is not just a uniform, it's also more assistive devices. The padded leather shoulder is going to be there to help distribute the load and reduce the immediate friction on the shoulders that comes from the use of the lifting beam assist. When I was reviewing this material with Dr. King, she quickly pointed out that not only are the leather jackets acting as a PPE to protect the shoulder, as a sort of form of padding, they're also allowing for a pivot to happen as well. When we have the standard solo lift of the keg, we have the given keg with two different centers of mass, the keg and the lifter, separated by some distance we'll call r. In order to turn the keg, you're going to need to apply some force sideways to the keg to pivot it about your center of mass. This means that you will have to apply a twisting motion at your back. In our tandem lift, we have the heavier mass of the barrel, but because it's suspended between two people, we now have 3 centers of mass instead of 2. We're still going to call the distance between the center of the person's mass and the barrel's mass r. And we're going to assume, just for simplicity's sake, that each person weighs about the same amount. So now, in order to induce that same twist about that pivot point of the barrel itself, the force to do the twist is now going to be split between the two operators. And not only that, that force is going to be evenly applied by them because of their protective shoulder padding. So thanks to this little pivot we have, we can actually also reduce massively the twisting force involved in moving kegs around things like corners. We should find it somewhat embarrassing that the 17th century brewhouse has more mechanical lifting aids in it than many modern craft brew pubs do today. There is both a pump in the midground. In the background, it looks like someone is using a sling and hoist to lift things, probably grains, up to the top of the brewery, but we also see that there's a lot of individuals working. Now, some of those individuals are doing tasks that we assign to pumps and other types of flow assist devices. However, the nature of teamwork here cannot be missed. There are many individuals available to do the work available, and there's many types of tasks to spell people off. The sleeping individual in the foreground is often a source for some merriment when people see this depiction. People often think that they're a drunk brewery employee who is simply sleeping it off. However, a lot of brewmasters who have run small brewery operations recognize that this person is likely the brewmaster. This is mostly evidenced by their age and their manner of dress, note the apron, but it's also because at this period, the brewmaster would likely have arrived first, started things like fires, and prepared things so that his novices could then take out the tasks of brewing. Having arrived first and early in the day, he is probably taking a well-deserved nap in preparation for his more complicated work handling the yeast later on. These base ideas of ergonomics were baked into brewery design. Here we have a London, England brewery rail yard from 1870. Not only do we see the barrels being rolled, but we notice also the height of the beer train, very similar to what we saw in the Guinness barrel yard. The train is lower than the loading platform so that full barrels can be rolled down into the cars, and only empty barrels are either rolled or lifted out. So even when we put package design, lifting technique aside, and even the use of assistive devices, even the architecture of the brewery emphasizes the ergonomics that are going to be at play. This is another thing that modern breweries miss out on, partly because modern breweries are usually retrofitted into existing structures. And retrofitting breweries into existing structures makes sense for all kinds of reasons, but when we do that, we tend to do the least amount possible because of the cost involved, not necessarily fully realizing the costs that we're incurring long term. This image was originally intended to advertise the enormous size of this London Porter brewery's aging barrel from the early 1800s. However, I'd like to examine the person working in the corner in a little bit more detail. Here we can clearly see the barrels being rolled on their sides and then finally placed on their end and not stacked. This individual is likely a male, but we can see that even in the 1800s we're still rolling barrels. In another one of these advertising brag depictions that we see from this period, we know that the barrels here are full size, 164 liters likely. And note, in no case are they being stacked, in every case they are being rolled, only finally at the end being placed on their ends so that they don't roll away. And when we talk about intelligent architecture, it doesn't just stop at the loading dock. Here we see the interior at a fermentation room in a London, UK porter brewery from the late 1700s. The cellar is quite large in size. The brewer that's depicted here is going to have to transit that barrel he's moving quite far. There's tile underneath all of the fermenters, and the floor generally slopes to the center. This is important as this style of brewery is likely to have yeast overflowing onto the floor. All combined, this means that the floor is likely to be slippery. Now, moving a heavy load across a slippery surface over a long distance is normally a recipe for injury and disaster. However, we know that this facility probably operated fairly reasonably. Again, likely due to the techniques involved in handling the products, less so than the actual packages and products themselves. When the volumes of liquid to move were too small for a barrel, buckets were often used instead. Featuring a handle and often carried in a balanced tandem style again, we see that the buckets provide a relatively centralized loading, even though the heavy wood of the bucket will mean that it is a significant weight even while empty. And of course, our labor supply in the past isn't coming from just people. There is heavy use of horses and ponies and donkeys to do all kinds of labor around breweries. A lot of the depictions we see of old breweries often show the animals as well. Fun side note on this is a lot of old beer delivery depictions show a tiny little dog accompanying the delivery person. My only assumption is that this could have been a guard dog. They're often not listed as part of the brewery's staff, nor as a requirement for delivering beer, and yet they are so ever-present. Many of the assistive devices we saw in previous slides were not powered by human power, sometimes not even by water power. They were often powered by equine sources: horses, ponies, donkeys, and mules. If you're used to looking at historical brewery records, you're used to seeing things that are a little incomplete. You see a lot of things that say, oh, well, the water was prepared in the typical fashion, or the barley was malted in the normal way, and there's just a lot of detail that gets left out. And you see that too with the use and descriptions of horses, or rather lack thereof. You see them in all the brewery advertisements pulling the wagons, but records on how many horses they kept and how they fed them, relatively hard to come by. Despite all that, the draft horse is a whole breed of horse specifically bred to handle the hauling of large quantities of beer in wagons and on sleighs. So this is another compounding factor. Not only do we see the use of lifting aids being quite common in a lot of the small breweries of the past, but those lifting aids are often not even being powered by people at all. And indeed, we see quite efficient uses of equine labor. Here we have a single draft horse pulling an entire canal boat. The efficiency of using the single equine engine to power that much beer is significantly more efficient than we see today. And, the solution to take from this isn't really that we should be moving beer by canal these days, but more so that you can make good, efficient use of available power, but sometimes you have to think about things a little bit differently. You can also see that the barge is almost at the same height as the riverbank next to it. This makes loading and unloading the barge relatively simple, at least at the beginning. As you unload the barge, it will float higher and higher out of the water, and thus you can then roll things off of the barge onto the shoreline. Now that we've discussed the problems of the present and looked at some of the solutions from the past, it's time for us to plan for the future and take a look at where do we go from here. No matter how cute it might be, obviously we can't breed tiny horses for use inside the brewery. We do need to, however, recognize the simple and straightforward fact that the standard size of beer keg is too large for a single individual to lift safely, particularly over the course of a career. It's also time to recognize how injurious and difficult keg lifting actually is, and to take that into consideration when we're planning our brewery and bar spaces, as well as our access to lifting aids, not to mention our attitudes. We must sadly recognize that the international standard for beer distribution is unlikely to change anytime soon. Likewise, our clients' needs aren't going to change anytime soon either. However, we do have craft breweries that are embracing 30, 20, and yes, even 10-liter kegs because of the inherent lifting issues. This includes some inherent inefficiencies. There's fewer liters per keg, which means more kegs per liter, which means more wasted shipping air, more wasted surface area, which leads to greater consumption of cleaning chemicals. However, the biggest difference is going to be for the front of house, because you're going to have a higher number of keg changes. However, you can daisy chain kegs together. One of the other things that we can do, even in the small brewery and in the brew pub, is we can consider our tasks and arrange our workflows such that we're not lifting the keg as often, that we consider lifting the keg to be something we are prioritizing against. So something that big breweries do is they track the number of touches. They track how many times an operator touches an individual product. And this is one of the ways they measure product handling efficiency. The greater number of times a product is touched by an operator, the more it costs you. So by reducing the number of touches, you reduce the overall cost of the product. However, this also applies to safety. The fewer times an operator interacts with a hazardous item, the fewer times we're going to have that hazard come back to haunt us. Tracking the number of touches is also something that can be done in the small brewery, and to much the same benefits. You still get financial benefits from touching the keg less because your operators have more time to do other tasks. You also get the same safety benefits. If a keg doesn't have as many times to be moved, you don't have as much time for injuries to develop because you're not doing as many lifts. Front of house cold rooms in particular are bad for repeated short interval keg moves, particularly when you have to rearrange kegs to get something closer to the tap because the hoses aren't long enough, or the hoses are tangled, or someone has inefficiently organized the keg room prior to your arrival. Aside from work attitudes and other organizational changes, architecture and interior design combine with these techniques to lead to a more efficient flow of beer through a building. You don't just want the beer to flow through the pipes and through the people, you also want it to go through the building. It's one of the ways you avoid cross streams, and it's one of the ways you handle product recalls much more efficiently as well. When we're talking about building architecture, something that's very helpful for tracking touches in workflow is something called a spaghetti diagram. It's where you draw arrows connecting where items come into a room, where they're moved through that room, and where they go out. Ideally, you have as few crossed lines as possible. Where lines cross, so do people. When people interact, when people cross, you're going to have more accidents, and you're also going to have more times when things need to be moved out of the way, or when workflows need to be briefly interrupted to accommodate other employees. You want to have as little crisscross as possible, and have more sort of straight noodles than a tangled spaghetti, hence the name of the diagram. Recognizing that a lot of brewery employees will still have to do the dangerous lifting, even perhaps knowing that they're not safe to do, we got some lifting tips from the experts for how to handle the most extreme loads that the body is supposed to handle in the workplace. You've probably heard in the past to lift with your knees. We now give a little bit different advice because lift with your knees was always a little bit vague. In particular, the curvature of the spine is part of what helps it bear loads properly. Keeping your spine curved, especially the lower spine, curved properly, helps the spurs on the back of your spine interlock to handle the heaviest loads. Put simply, the advice is to stick your bum out. You need to bend from the hips and the knees rather than from the low back, keeping your bum bent outwards. This keeps the joints in the vertebrae together, supporting the load rather than putting all the load on your intervertebral discs. We're now going to briefly touch on some of the ways we can use to determine what safe loading for an operator actually is. Safe loads in this case will refer as much to the frequency of the lifts as it will to the size and nature of the lifts themselves. Try not to be too intimidated by this slide. This is called the REBA Employee Assessment Worksheet, and it looks at all different types of movements that an operator might have to do during their day. So this one looks at not just lifting, but different types of, say, crouching, perching over, and different types of wrist movements that an employee might have to do. So this is actually a very valuable resource if you're looking at putting together a packaging line as well. At the bottom of the slide, we see some of the tools we can use to do the assessment. There's both the option of using complicated video cameras and motion capture, as well as the much cheaper method of simply using your eyes and best estimates. REBA sits somewhere in the middle. It's a little bit closer to the eyeballing side of things. The key in REBA is the rapid entire body assessment. It's there to give you a quick idea as to something that's probably okay and something that maybe needs some review. This chart here shows the different factors that affect what our safe lifting limit is. This takes into account a number of different factors, but most importantly, how many lifts you're doing in a day. The biomechanical limit is what you can do before your body starts damaging itself. Specifically, it's what you can output before you start really compressing those squishy discs. Not just scarring the surface, but actually changing their shape. Note that you can execute lifts that will do this type of damage, and that's why there's multiple limits on this chart. Which is why this biomechanical limit is above the physiological limit, indicated by the blue arrows. The physiological limit comes from the body's plumbing, your cardiovascular system. At that point, your body simply doesn't have enough throughput to be able to actually keep up with the repeated pace of loading. So the physiological limit is very much related to how good your cardio system is and how many of these complicated lifts you can do in a day. So it's the body's ability to supply fresh oxygen and other chemicals and also remove waste products that is key to the physiological limit. The yellow arrows indicate the psychophysical limit, and this is what feels safe for you to lift. You may notice, of course, these limits are actually quite different to each other. So our safe lifting limit that we want to apply in the workplace is the least of all these. Okay, we want to go below all of those curves, and this is indicated by the green arrows. These limits are going to be fundamentally estimates based on our best ways that we measure the human body and the human capacity to output work and the loading it can take. For low frequency lifts, these are lifts that we do very rarely. The biomechanical limit is conservative. Okay, so for rare instances where you may have to move, say, some Christmas stuff, a seasonal item up onto a high shelf, it's a very low frequency lift. So the relative risk that poses to a worker is comparatively low. The high frequency lifts are where the physiological limit is conservative. Okay, so we want to be below the physiological limit for some of those tasks that we do very, very often. The danger zone comes where our psychophysical limit, the one that we feel is safe, is above the curve of the safe zone for our lifting. Okay, so you have to be aware to stay out of the danger zone and stay in the green part of the curve. When you climb above 3 lifts per hour, you start to get into the territory where the psychophysical limit is actually a slight overestimate of what the physiological limit is. So if you have, say, a production lineup and you're doing an activity more than 3 times per hour and you're having workers coming to you saying, I think this is hurting me, they're probably telling the truth. It probably is hurting them, and in fact, you can probably scale back well below what they think is safe because of the nature of accumulated damage. So provided we keep the size of the lift and the frequency of the lift low enough that it stays in the green zone of this chart, we're going to avoid doing the type of long-term damage that we're worried about here. Now, what this chart doesn't look at is other things that can impact the safety of a workplace. You know, if a lift is being done at the top of a tall ladder, next to moving machinery, even done with the wrong footwear, there are other things that could make an activity unsafe. However, this is looking at just our loading and how often we're doing that loading. Tables like these are used to examine how safe a high-frequency lift or action is going to be, right? So if you're doing a pull or a push every, say, 5 minutes, it'll give you a different load for if you're doing the same push or pull every 30 minutes. You don't need to memorize or be that familiar with these tables. You need to know they exist and that you might have to use them sometime. So the last slide actually examined pull type of loads, and these ones look at actual lifts and carries. These charts are maybe not the best ones to use for our keg lifting, because our keg lifting is frankly well outside the bounds of most definitions of safe lifting. But there may be solutions available today to help us combat some of the awkward lifting scenarios that we see. So Dr. King was actually kind enough to let me try out one of these cool new exoskeletons that they're trying to put forward for PSWs in their awkward workplace lifts. I found this personally to be extremely helpful and very much relieving of the type of back pain I experience. This video shows me executing a fairly simple lift. The box is considered to be a slightly awkward dimension to lift, and the weight is approximately medium. However, this shows you the type of range of motion you can go through. This is a passive type of support system. There's no motor involved. There's only a spring-wound steel cable that is controlled by a clutch on your shoulder. You set your preferred working height, activate the clutch, and then the steel cable engages to transfer the load from your shoulders and upper back around the exoskeleton and down to your thighs. The human body is still outputting all the labor required to do this task. I won't lie, they're not exactly stylish. It's definitely a workplace type item. They're not that uncomfortable to wear. I didn't feel uncomfortable wearing one sitting at a desk for approximately half an hour. The smile you see on my face in the last photo there is partly because I had not bent over without my body making a popping noise in longer than I care to mention until I tried out one of these things. So if you're interested in this exact type of unit, I'm not getting paid or anything by them. It's a HeroWare brand unit, and I believe it's a startup company that's a partnership with a university in the United States. I also do apologize for the socks rather than proper shoes in this video. I had to jump on the opportunity to try this before they were shipped out from Dr. King's home, and in the course of doing that, I had to try them right away, indoors. So let's try to bring this train into the station. Let's have some final thoughts to consider. I think it's worth asking, can we do better? It's long past time that we examined our relationship with the half-barrel keg, consider how we supply draft beer, and ask that critical question, can we do better? It will be a long time before there's an affordable robot that can easily navigate a bar's back room, but some of these people assist options might be right around the corner. And always remember that protecting the employees you have is almost always cheaper than designing and purchasing a robot that you don't have. So as we leave this topic, I hope you've taken some time to consider what some of the different approaches that we can use to address these issues, namely how we move kegs in the first place, whether or not we're moving the right size of kegs, how many people we assign to the job, how much we expect them to do of that job in a given day, and notably, what some of the other solutions to this might be. And with that, I'll leave you. Thanks for watching, stay safe, and once again, a big thanks to the talented Dr. Emily King, the well-read Alan Brown, and the incomparable DJ Steele. Once again, I'm Matt Phillip. Thanks for watching.